It's my great pleasure to introduce for us today our seminar speaker, Brandon Hensley. I think that actually, like on average, you are also from Nebraska, much like myself.
On average.
Yeah, on average. And then he got his undergrad at Caltech, and then he went and did his PhD at Princeton. After that, he was a postdoc fellow at JPL, also LA area. After which he went and did a Spitzer Fellowship, also again in Princeton, and now he is back at JPL as a research scientist. So, on average, he's a Midwesterner. It's a good stats problem for somebody somewhere. He is really cool. He's a great expert on interstellar dust. Every time I hear him talk, I learn some nugget of information about dust that just blows my mind. And so I'm really glad to have him here. And it seems like a lot of you have also been enjoying a lot of conversations with him. So without any further ado, I will let him take it away.
All right. Thank you so much, Justin. Well, it has been an absolute pleasure visiting here so far. I've had, as you said, lots of conversations today on a range of topics, and it's just been a lot of fun. So I'm really looking forward. I'll be here through the end of the day tomorrow and with all of you. So, your seminar organizers have organized a talk on interstellar dust, and so that's what this is going to be. So fair warning, this talk will be very dusty, but I will try to bring in some disparate threads, including cosmology, because I do think that whether we're talking about galaxy evolution or whether we're really even talking about observing the birth of the universe, we have to understand interstellar dust to be able to do so. But I'll talk a bit more about that. But first, I would want to dive straight into the dusty goodness and talk about what I mean when I talk about dust. So when I say interstellar dust, I refer to the solids that live in interstellar space. So dust grains are the reservoirs of carbon and oxygen and magnesium and silicon and iron and trace amounts of the other heavy elements in space. And these dust grains are not all that different than the kind of dust grains that we're familiar with terrestrially, except they are a bit smaller. So dust grains range in size from a few hundred nanometers, which is actually about the size of viruses, if that is a meaningful comparison, all the way down to where we can start arguing whether we're talking about dust grains or we're talking about molecules. So things with maybe 30 or 40 atoms. I'll be talking a lot about things in that category today. And so typical life of a dust grain, it's sitting in the interstellar medium. It absorbs a starlight photon in the UV or optical that heats it up. And so the typical large 100 nanometer dust grain will sit there at about 20 Kelvin and radiate that energy in the far infrared. Characteristic temperature, like I said, about 20 Kelvin. So that's just kind of to set the stage of what I mean when I talk about dust. But why do we study dust? What is the thing that gets me out of bed in the morning to think about specks of dust in interstellar space? So one of my major motivations for this is the fact that we are having this talk on the surface of a giant dust grain, that all of the solid bodies in our solar system are from the agglomeration of innumerable tiny dust grains from the interstellar medium that have found each other coagulated into these macroscopic solid bodies. So comets, so asteroids, so planets all have their origins in the dust grains in interstellar space. And what I want to do is to understand the life cycle, the trajectory of dust in diffuse space all the way through its formation into solid bodies. But it's even more than just that. Dust grains are also the site of chemistry. So most of the ice in the universe exists on the surfaces of dust grains in molecular clouds. So not just water ice, but also carbon monoxide and carbon dioxide. Also, most of the molecular hydrogen in the universe was formed on the surfaces of dust grains. So dust grain, a hydrogen atom sticks, it wanders around until it finds another hydrogen atom on the surface. They bind, and that binding energy liberates the H2 molecule from the surface, giving us molecular hydrogen. So even if you wanted to ask the question of where do stars come from, dust grains are a necessary ingredient to build up those molecular clouds that will eventually form stars. So whether you're talking about the formation of stars, or the formation of planets, or even the formation of complex organic molecules, dust grains play important roles in each of those processes. Understand that. But it does not suffice for me to just talk about stars and planets and organic molecules. Let's talk about the universe. So if we want to study the birth of the universe, one of the most sought after signals in early universe cosmology right now is a signature from primordial gravitational waves. These are gravitational waves that were propagating during the epoch of inflation, where the universe expanded in size by many, many, many orders of magnitude. And these gravitational waves leave their imprint on the cosmic microwave background, and in particular, its polarization patterns. They imprint what we call a so-called B-mode polarization. So it looks essentially, like if you think about electric and magnetic fields, it looks kind of like a magnetic field, sort of a divergence-free pattern. And if we were to detect this pattern in the polarized CMB, the amplitude of the signal would immediately tell us what the energy scale of the inflation process was and give us one of our first direct insights into the nature of quantum gravity. So this has launched a large number of cosmic microwave background experiments that are all studying the microwave sky in exquisite detail in polarization. To go after the signal, it's faint. You need to build telescopes that are large in some of the best observing locations in the world, such as the Chilean Atacama or Antarctica. You just field them with tens of thousands, if not hundreds of thousands of detectors. They're all exquisitely calibrated. But even once you've done all that, there's another very large problem for detecting the signal. And that's that this B-mode polarization is not just produced by gravitational waves from the birth of the universe. That little dust grains that live in our own Milky Way galaxy can also produce this B-mode polarization. And so in fact, in 2014, there was a claimed detection of the primordial gravitational wave signal that had to be retracted a few months later when everyone came to realize that what they had seen was not these primordial gravitational waves, but rather the dust grains that live in the Milky Way. So if we want to go after these inflationary signals and learn about the very birth of our universe, we need to understand something about the dust that lives in our own galaxy. And of course, there's everything in between our solar system and the edge of the universe. I also like to think about dust as a probe of galaxy evolution. So particularly with the James Webb Space Telescope, with ALMA, dust has become a powerful way to observe galaxies. And we need to be able to do the translation from these dust observables to what does that tell us about the properties of the galaxies themselves. So, how can far infrared emission from dust grains tell us something about the galaxy in which it resides? So in some sense, dust bears witness to the whole galaxy evolution process, from the formation of stars to mergers. It's sensitive to the radiative environment, it's sensitive to the density field. And so all of these things must leave their imprint in the dust observables. And it's a matter of figuring out how to extract that information to let dust grains tell us something about the evolution of galaxies through cosmic time. And so it's for all three of those reasons that I get out of bed in the morning to study interstellar dust. And unfortunately, in this talk, I'm not going to be able to go into each of these areas in any amount of detail. So I've decided to focus this talk on two stories that I hope will be illustrative of the power of interstellar dust, if you want to phrase it that way. I'm going to start by talking about polycyclic aromatic hydrocarbons, and I'll introduce those in a second, and thinking about how they form and how they grow. And then the second one, I'll tackle a fairly big question, what is dust made out of? And I think that we kind of know the answer to that. I told you, carbon and oxygen and magnesium and silicon and iron, but rather, not just the constituent ingredients, but rather how they're combined. What does a dust grain actually look like? And I will connect both of those separately and together back into big questions of import for cosmology as well. Okay, so I should say that you should feel free to stop and interrupt me at any point. I'm super happy to field questions as they arise. Okay, so let's dive in. So I want to start by talking about polycyclic aromatic hydrocarbons, PAHs, as some people call them. And these are really the smallest end of what we would consider part of interstellar dust. In fact, you have some people who will argue that we should not think about them as dust at all. They are molecules. So I'm happy to be inclusive and call them dust grains. But we're really talking about things that are maybe only 30 atoms, carbon atoms in size, maybe up to about 1,000. So this is actually below the size cutoff coordinate here, but it kind of gives you an illustrative idea of what these things look like. So benzene rings attached to one another. Maybe you'll have a little side chain, hydrocarbon side chain hanging off. Maybe some of those carbons will get substituted by nitrogen. But you know, the general idea is they look something like that. And these molecules emit very strongly in the mid-infrared. So here's just a mid-infrared spectrum that's synthesized from some Akari and Spitzer data that show you these emission features from these molecules. And all these are just various vibrational modes in these molecules. So if you have an aromatic ring and you have a hydrogen attached to it, it can do like an in-plane stretch or an out-of-plane bend. You can also have bending of the rings themselves. And each one of those types of modes integrated over a whole class of molecules give you these very broad features. But you notice that the wavelength scale here goes from 2 to 40 microns. So these are extremely short wavelengths. If you're going to emit thermal vibrational radiation at such short wavelengths, you need to be heated to an extraordinarily high temperature. We're talking hundreds of Kelvin, which is quite a far cry from the 20 Kelvin I mentioned just a few minutes ago. So how does that work? Well, these things are so small, they have basically no heat capacity whatsoever. So a UV photon comes in, interacts with the grain absorbs it, it raises its internal energy, just that one photon, up to 1,000 Kelvin, and then it radiates that energy in these vibrational modes in the infrared. It's what we call single photon heating or stochastic heating. Okay, so these are the PHs. They're generally best known through their emission features. Where do the PHs come from? Well, I think it's pretty definitive that they are created in stellar outflows. We see PAHs around HEB stars, also see them around Wolf-Rayet A stars. So this is a James Webb Space Telescope image of Wolf-Rayet A star 140. So the spikes you see here are just diffraction pattern spikes from JWST, so it's an instrumental artifact. But these rings are real. This is not instrumental. This is a star that has a binary companion, and every so often it just blows out a spherical plume of gas and dust. And so it's a perfectly spaced timings, and you just see these concentric rings around the star. And in these rings, we see the evidence of these pH molecules. So they're clearly being formed and condensing out of these stellar outflows. So we know that stars can make PHs. It's also the case, probably, I think the evidence is pretty convincing to me at this point, that you can also get these PHs from the gas phase, so build them up, essentially atom by atom in dense gas. But you need really dense gas to be able to get chemistry this complex. So we're really talking about the very centers of a dense core, not something that would ever go on in the diffuse interstellar medium. And then finally, I think there's good evidence, just thinking about this as a lifestyle thing, that the PHs are destroyed by ionizing radiation. So if you go inside of an H2 region, we tend to see a deficit of these pH molecules, probably because the high energy photons are able to break even these aromatic bonds. So JWST has really blown open the field of PAHs. So this is a postage stamp that was issued showing MIRI observations of NGC 628. And all of this beautiful structure in this galaxy that you're seeing in this image is from PAH molecules. So PAHs have now been on US postage. Very and so this is a big opportunity to not just learn about the pH microphysics, but also to think about how to use PAHs as a diagnostic tool to understand what is going on in these galaxies. What is the UV field that is deciding these PAHs? What are the chemical processes that produce these PAHs? And so on. And indeed, so the pH emission spectrum can account for about 20% of the total infrared luminosity of a galaxy, a typical star-forming galaxy. We also are now seeing PHs at high redshifts. This is an image that might be familiar to some or many in this room. So this is a 3.3 micron pH feature observed in a Z redshift 4.2 lens galaxy. And the striking thing about this is that Z of 4.2 corresponds to when the universe was only 1.5 billion years old. And already this starts to make me a little bit uncomfortable because that's not a lot of time to build up PHs to give you a booming signal in a galaxy like this, especially if you have to create all of your PHs from old massive stars that take a lot of time to evolve. So already, amazing that we're seeing this, but already as a theorist, I'm like, uh-oh, how are we going to get all these PHs in these early galaxies? It turns out that emission is not the only way that we can see PHs. There is also extinction. And so this is a plot of the extinction curve of the Milky Way. So extinction is just how well dust absorbs and scatters light, the sum of the absorption and scattering cross sections. And now this is plotted from 0.1 microns, so this is the UV, all the way out to 40 microns into the mid-infrared here, and in total in black and polarized in red. And I sadly will ignore the polarized extinction for now, but if you want to talk to me about polarized extinction, I will gladly talk your ear off on it. Let's take a peek at the total extinction now. You see there's a lot of features in here. Just as we saw those emission features, there's a lot going on here. And it turns out that some of these are related to PHs, or at least to aromatic material. Now, the one I'm really going to be focusing on today is this bump here at 2175 angstroms that is probably caused by PHs. It's almost certainly caused by hydrocarbon nanoparticles of some type. We see in the laboratory features like this associated with sp2 bonded carbon, the kind that you would see in a PAH backbone. It's also essentially no scattering has been observed in this feature, so you can look in like reflection nebulae. And so the fact that there's no scattering tells you that the particles are probably very small relative to the wavelength. And so PAHs kind of tick both of those boxes. So if we know something about this 2175 angstrom feature, we might know something about the PAHs. And if you really, really squint, there's also some additional hydrocarbon features here between about 3 and 10 microns here in the extinction curve. I won't dig into those in too much detail, but there's other fingerprints of aromatic material and also aliphatics or chain-line hydrocarbon material. I want to zoom in on this bump because it will be very important for the things I'm going to talk about. In my view of dust, we have what I'll refer to now as just like the rest of the dust here in red and the PAHs here in blue. And you see that they are both contributing at the wavelength of this bump. So the actual bump feature itself is caused by the PAHs. There's non-negligible extinction from the other kinds of grains. Also, apologies. The x-axis is in inverse microns because that's how people like to plot the UV. I hope this will be the only non-intuitive unit in the rest of the talk, but no promises. So anyway, UV here, optical here. So you see that this UV bump's shape is caused by the PAHs, but the other grains give us extinction too. And even in the optical B and V bands, you see that the PAHs are contributing a little bit to that. Going back to high redshift galaxies, so not only do we see PAHs in emission at high redshift, we also see PAHs in absorption. This has now been seen in at least a half dozen or so galaxies. I just picked a recent one here, showing this telltale 2175 angstrom-ish bumps. This one's at 2257 for some reason. They also offset, and I don't quite understand that. But, about the right shape. Consistent with what we see in the Milky Way, and this is at a redshift of 7.1, I believe, and the universe was only 750 mega years old at this stage. So another factor of 2 down from the Z of 4 pH feature that we saw. So again, there's so little time to be able to form these PHs, and yet we're seeing these fingerprints in their extinction curve. So where is that coming from? Okay, so that was one extinction mystery, but I actually want to spend the next 10 minutes or so talking about a different extinction mystery and then maybe connect them back up at the end. So I have shown you the Milky Way extinction law and its wavelength dependence, and we often parameterize its wavelength dependence by this RV parameter, which is the extinction in the V band divided by the difference in the extinction between the B and V band. I lied about there being no more unintuitive units. Apologies for that. But basically, this RV just tells you what the slope of the optical extinction is. And the lower, just if it's RV has a low value, it's a very steep curve. And if RV has a high value, it's a very flat curve. And just to kind of give you a sense of numbers that we talk about, the diffuse interstellar medium has a typical RV of 3.1, and dense clouds have up to 5.5. Generally, we think that is kind of the normal range. But
Are you going to talk also about objects that have RSV of like 1.5?
I'm not going to address them explicitly, but I think what I'm going to say might be relevant to them. So
it's certainly relevant to supernova surveys.
Let's revisit this. Yeah. And we know that this RV value varies over the sky. So if you ask what the lore is for why does this RV value vary, it all goes back to the size distribution of interstellar grains. That as you have a molecular cloud of some kind, you go into the cloud. As you go into the cloud, your dust grains get bigger and bigger and bigger as more stuff sticks onto them and as they stick to each other. As the dust grains get bigger, you have more grains that are big relative to the wavelengths at optical wavelengths. And if you have a particle that's big compared to the wavelength, that gives you a very flat extinction curve. So as you push your grains to bigger and bigger sizes, your extinction curves get flatter and flatter, and RV goes up and up. So that's just illustrated in a model here from Weingartner and Drain, 2001, that as you push your peak of your size distribution to larger and larger grains, you increase your RV value. And that has been the lore. However, there is an extinction mystery that was uncovered, and that's all due to Gaia. So Gaia satellite has been an amazing gift to astronomy in a number of ways. But one of these ways is that there are 130 million plus stars that have F and G stars that have full spectra that Shangyu Zhang and his advisor Greg Green at MPIA used to construct full 3D maps of the interstellar extinction across the full sky, but not just the total amount of extinction, which gives you a 3D dust map of the galaxy, but also this RV parameter. This is how the extinction curves varies. And that is the first time that we have ever had a full sky map of this RV parameter to understand what actually drives these extinction curve variations. So Shangyu's work made the cover of Science back in March. I was very pleased to see interstellar dust in big letters on the cover of Science magazine. So very happy about that. But some months before that, Shangyu visited me because he had a mystery that he was seeing in his data that he wanted to see if we were able to solve. So, when you measure 130 million things, some anomalies will tend to crop up. And here's one of them. So this is in the cloud Perseus. I have RV plotted here on the y-axis. And on the x-axis here, I have the total amount of extinction. So you can just think about the x-axis as you go further down, you go deeper and deeper into this cloud. And so the classic picture that everybody would have had and the prediction they would have made, as you go deeper and deeper into this cloud, your RV value should go from 3.1-ish from the diffuse medium and go up to something like 5.5 when you get very deep into the cloud. Your RV should go up. And what they saw was that actually, on this edge of the cloud, the RV seems to go down. And at some point, it turns around and goes back up. But there's this little piece where RV goes down. Okay, well, this is really noisy. One cloud. This is real. Look at Orion. See the same thing in Orion. RV starts at 3.2 and goes down to 2.8 and change, and then turns around and goes back up. And so for those of you familiar with this, this is over an AV range of about 1 to 3. So kind of the translucent outskirts of a molecular cloud. And really, every cloud looked at, see the strange behavior where the RV seems to go down and then turn around and go back up. So, what could this be? Well, I teed this up with 10 minutes of talking about PAHs. So you maybe have correctly guessed that might be the answer to this question. But we decided to look to see if there was a PH connection using full sky maps of PAHs with the WISE satellite. So the WISE band 3, in the shaded blue here, covers a number of these PAH features. And you can use these data. So this is just the WISE 3 diffuse emission map from Meissner and Finkbeiner. You can use that to compute the relative abundance of PAHs. So essentially, you take the total emission in WISE 3 and then you normalize by your total far infrared emission. And that gives you how bright your PAHs are relative to the rest of the dust. And that gives us this so-called QPH factor. It just tells us how abundant the PAHs are as a total mass fraction of dust. And what we saw when we plotted our RVs against this QPH factor was a strong negative correlation in every single cloud we looked at. That as the PAH abundance went up and up and up, as we went into and into the cloud, RV went down and down and down and down. So the more PAHs we had, the steeper our extinction curve. And if you go back to this plot, and comes actually explainable why, because if you're saying what I'm doing is changing my pH abundance, then I'm holding this red curve fixed, and I'm taking this blue curve and I'm just shifting it up. And as I shift that blue curve up, I am making a big contribution to the extinction in B band and much less of a contribution to the extinction in V band. And so my extinction curve gets steeper. So if I move this curve up by a factor of roughly 2 or so, I can explain the full range of RV variations that we're seeing in these clouds. So I was skeptical at first, because what this means, is this is right, is that we're seeing these PHs growing in real time in these translucent regions of these clouds. Can this make any sense whatsoever? This was not part of the standard pH lore. But it does, because the pHs are small, but they're very abundant. So they actually have most of the grain surface area. So carbon atoms in the gas will be preferentially accreting to the pHs. And the time between collisions of carbon atoms and pHs is actually pretty short. So, carbon atoms and pHs must be exchanging carbon, so the gas phase and the solid phase must be exchanging carbon atoms on a reasonably quick rate. So as you go into these clouds, maybe you're just shutting off your UV photons that are knocking out carbon atoms. The grains are able to hold onto their carbon atoms a little bit better. Things stick for longer, and the pHs grow and grow, such that you're turning carbon atoms from the gas into aromatic material onto the dust grains. And it turns out that the amount of growth that you need to change RV by the amount that we see essentially perfectly agree with these changes in these QPH parameters. It really was about a factor of 2 in our pH abundance, able to explain these RV variations, and any QPH change by a factor of 2 from the lines data. So,
sorry, that sounds like that shifts the distribution of PAHs from the small ones to big ones, but not necessarily like increases the overall abundance of PAHs, unless you're forming new small
you're forming new. So I'm arguing that you are taking gas atoms and you are turning them into dust atoms. And you have maybe 40 ppm of carbon in the solid phase to begin with, and by the end of this process, you maybe have 80. So I really am talking about growing from the gas phase. And the other beautiful thing about the optics that goes on here is that even a pH that is grown by a factor of 2, we're still talking about tens or maybe hundreds of atoms. It's going to be very small relative to these wavelengths. So the strength of this feature and the shape of this feature completely doesn't care what your size distribution is. It just cares about the total amount of mass that you have in pHs. So the fact that you're shifting around the size distribution, you can shift it around all you want. It just cares about the total mass, and this feature will scale in strength proportional to that amount of mass.
So then maybe to Kevin's point, it seems like there's basically like a bracket to the range of RV that you could possibly get, one where you have 0 pHs and one where it's like that's the dominant contributor to the total extinction.
So it's interesting. So a lot of people will quote the Rayleigh scattering limit as the ultimate limit on this. But I mean, here, this is a pure absorption feature. So it actually is entirely set by the dielectric function of this material, the absorption properties. So that you can have whatever RV you wanted as long as it's So kind of putting this together, my revised heuristic pH lifecycle story is that we do have pH injection into the ISM by evolved stars. In the diffuse ISM, you really need to be 30 atoms or bigger to be able to survive the harsh UV irradiation of the diffuse ISM. But then the new thing, in this moderate density gas, you can actually have accretion of carbon from the gas onto your pHs to make them grow. And it probably does shift the pH size distribution to somewhat larger grains, and makes the pHs overall just more abundant. And then in the very high density gas, for much higher density than what I showed you on these previous plots, you could have this bottom-up formation process where you're actually doing gas phase chemistry to form the pHs. So in this view, you could have just a little bit of injection into the ISM by evolved stars. So maybe some rare class of massive star that evolves quickly and spits out some pH seeds into the interstellar medium. But then if you have this moderate density process occurring, you might be able to grow your pHs enough to explain these JWST results without having to invoke any exotic scenarios for how they got there. So I think this could be an important key to figuring out why the universe is so pH enriched so early. Okay, so that was a tie into galaxy evolution, but I want to talk about cosmology. So we think about extinction in the context of cosmology many different ways, but one of which is galaxy surveys, where you're trying to map out the large-scale structure of the universe to infer things like what is the nature of dark energy and has it changed over time? What is the matter content of the universe? And so on. But anytime that you're trying to do measurements, precise measurements with 3D galaxy distributions, you care very much about anything that alters the apparent abundance of galaxies. And one thing that does that is interstellar dust extinction from our own Milky Way that makes things fainter than they actually are. So, you will lose some to your, the color selections or other magnitude selections that you make. So if you need to know exactly how your dust is changing the intrinsic properties of your galaxies to be able to account for this effect and not mess up your cosmological inferences. And so this is a map of residuals between kind of two of the best dust extinction maps on the market right now. So the Schlegel-Finkbeiner-Davis 98, the classic for the last 3 decades workhorse in interstellar dust extinction, basically made by looking at the infrared emission from dust grains and making a correction saying, if I know the emission, I can estimate the extinction. And then the other contender that has recently come online is from the DESI collaboration, who used stellar spectroscopy itself as a direct way to measure stellar reddening. So fitting an intrinsic stellar spectrum plus a reddening law to every star in their sample, and thereby creating a star-by-star reddening map and then averaging that. And what we see is that, overall they agree quite well. I mean, this is plus or minus 50 millimagnitudes. So for a lot of purposes, this is better than you'll ever need. But for precision cosmology, that's not true. So there was a very interesting study from the DESI collaboration, Karim et al. Just earlier this year, where they did a cosmological analysis where they were constraining the omega matter versus S8, so amount of clumpiness of the universe, if you don't think of it that way. And they did a test where they just swapped out these two dust maps for each other. And what they found was that going from the SFD to the DESI basically erased their tension with CMB measurements in the omega matter S8 plane. So we are now at the stage where dust reddening systematics are one of the most important pieces of the error budget in precision cosmology for galaxy surveys. And so we actually need to dig into what's going on with the differences in these maps. So I don't have an explanation for all of the differences in these maps, but this one particular region over here in Ursa Major stands out, and I think I can explain that one. So this is work led by my postdoc Dennis Lee at JPL, where indeed this is a region where we see a big change in the PAH abundance. And so what I'm plotting here is I take a galaxy sample and just count how many galaxies with these certain color characteristics are in a given square degree on the sky. Galaxies are isotropic. I should get the same number of galaxies in every little patch on the sky. But of course, that's not true because the galactic extinction affects these color cuts. So I need to make that correction. And if I've done that perfectly, I'll end up with a completely isotropic map. But if there's something wrong with my dust map, then my galaxy counts will not be isotropic anymore. And so what's plotted on the y-axis is the number of galaxies per square degree in a pixel. And then on the x-axis here is our favorite QPH parameter that we've been seeing. And what we found is in this region, there's a huge correlation between the QPH parameter and your galaxy count if you've done your dust corrections with the SFD map, or indeed any other far infrared map. And the reason is PHs emit all of their emission in the mid-infrared, They affect the far infrared basically zero, but we've just heard that they affect the total amount of optical extinction. So if you have a map that's completely insensitive to your PHs, you will never be able to constrain the contribution of the PHs to your optical extinction. And so we showed that something like WISE-3 is much less sensitive to this. And in fact, the very best you could do is actually to combine SFD and WISE. The far infrared plus the mid infrared gives you the ultimate extinction map that works even better than the stellar ones. So pH abundance also factoring into precision cosmology of galaxies. This situation might actually get a lot better soon. So the WISE maps are great. But the SphereX maps, I think, will be even greater. So SphereX, the NASA mission that was launched just a few months ago, is observing the full sky in 102 spectrophotometric bands between 0.75 and 5 microns. So it's going to do a lot of great ice science, looking at water and CO and CO2 ice in the mid-infrared. But it also covers this 3.3 micron pH emission feature over the full sky, in every single pixel on the sky. So here's the early SphereX 3.3 micron pH emission map of star-forming nebula in the LMC. So our understanding of PHs and their life cycle are about to get a huge upgrade with all these great SphereX data that are coming down. They do a full sky survey every 6 months, and they'll do 4 of those in their nominal lifetime. So a big chunk of those data are already on the archive and ready for anybody to look at and use. Okay, so I've done my pH spiel, and I want to take 15 minutes or so to go through the part 2 of my talk, what is dust made of? But first, let me ask, are there any questions on the pH side of things?
You scared me into silence.
Excellent.
Follow up tomorrow.
I had a question about the mega matter sigma thing. You said that brings them into agreements.
Yes, so with the Planck CMB.
Oh, okay. So
Yeah, so if, with the standard analysis using the SFD map, there was a, I don't know, kind of 2-ish sigma tension. It's like, is this real or not? And then when they plugged in the DESI map, it went to less than a sigma.
okay.
So yeah, it made a sort of 1-ish sigma correction to the contours.
Do any better if you like, instead of, I think you should like the Planck 857 map. Could you do any better if you like looked at the dust temperature or something like that? Is there something else that's with the PA abundance used from the far IR alone?
The accords with the abundance, I think, would be tricky because it really does seem to be a separate thing, especially if it's one of those things where it's like the abundance is changing, you know, in this kind of translucent gas, or it kind of depends on the evolutionary history of this parcel of gas. You know, if it was recently ionized and has cooled down, then maybe it's deficient in pHs. It's hard to see how that would get imprinted on the far infrared. So I think you probably need both. So we have both.
You do.
Okay, so the question I want to answer in this last part of the talk is, if I pluck a grain from the interstellar medium, what would it look like? So there's a classic answer to this. So the classic dust model looks like this. So we have silicate grains, acidic grains, or hydrocarbon grains, and then we have the PHs. And the idea was that if you have an AGB star that is oxygen rich, then all of the carbon gets bound up into CO, because C and O have a very high affinity for one another. You get a bunch of leftover oxygen that can make silicate type materials, MgSiO stuff. Contrarily, if you have a carbon-rich AGB star, then all the oxygen gets bound up into CO, and you have a bunch of carbon left over. You can make carbonaceous type dust grains. So you have silicate dust that's made from oxygen-rich stars, hydrocarbon dust that's made from carbon-rich stars, and then pHs we've already talked about. And so the idea is we had 2 separate grain combinations. If I plucked a grain from the interstellar medium, I had some probability of picking, oh, this was a silicate grain, and some probability this is a graphite grain. Okay, so now I need to talk about polarization. And I promised the graduate students there would be football, so there it is. So I like to think about interstellar dust grains as football because the rotational dynamics are actually very intuitive. So if I try to throw a football, it does a really great job of flopping over like this, because that's the way it wants to spin. Things like to rotate around their short axes. If you want to throw a nice spiral like a college football quarterback, it's actually kind of hard Take some skill. So dust grains don't like to spin like that. They like to spin around their short axes. And they also like to spin with rotation axis parallel to magnetic field lines. You could imagine this as your grain has any kind of paramagnetic material in it, then the induced magnetization is going to want to respond to a rotating magnetic field in its frame. The only frame where you don't have a rotating magnetic field is rotation aligned with B. And any other frame, you get dissipation from being unable to respond instantaneously to the rotating field. So the net result of this, grains spin around their short axes. The short axes are the rotation axes, and that aligns with magnetic fields. So grains align with magnetic fields, and they produce polarized radiation as they like to emit preferentially photons with electric field along the long axis of the dust grain. That's why I like photons. So this idea of two separate grain components gives us a very distinct polarization prediction. So if I have two different kinds of materials, they'll have their own optical constants and their own polarization efficiencies. They'll even come to different temperatures under the same interstellar radiation field, just like you imagine a grain of sand versus a hunk of coal set them out on the sidewalk on a hot day, they'll feel different to the touch. They're made out of different stuff. So the idea is that the total emission from both components would look different than the total polarized emission from both components. That if I plotted the polarization fraction as a function of wavelength at short wavelengths, the conventional story would go that I have the warm hydrocarbon dust. Imagine that coal would run warmer than a silicate type thing. And also it's less paramagnetic, so it's less good at polarizing. So at short wavelengths, I'm dominated by something that's hot and not very good at polarizing. At short wavelengths, I'm dominated by something that's cold and pretty good at polarizing. So I would expect that if I plotted the polarization fraction versus wavelength, I would get some serious frequency or some wavelength dependence in here. And generally, any kind of two-component model I would write down, unless I just finely tune them to have exactly the same SEDs or finely tune them to have exactly the same polarization efficiencies, would generically have a frequency dependence in the space. And that's not what we saw. So we finally got our first measurements of the polarization fraction from the Planck satellite here in blue and from the blast pole balloon here in red. It looks really flat. There's essentially no wavelength dependence whatsoever between about 250 microns and a few millimeters. And it's really hard to reconcile that with these two component models. So if I just run like the classic pre-Planck carbonaceous silicate model through those points, you see it does a very poor job. So the question is, do I really need two components? Do we really have two components of the interstellar medium? That maybe we don't actually have two components after all, it's all just one. So this is what I call astrodust. It made an appearance earlier on my extinction curve plots. And the idea is simple, that instead of having these separate silicate and hydrocarbon grains, we have composite grains that have mixes of the silicate and hydrocarbon material all just on the same grain. The two distinct grain populations in the old picture, in the new picture, everything gets homogenized. We'll say this is an artist's impression. I would expect things to be kind of nano domain on a hundreds of nanometer wavelength, radius grain. So the number of domains that you would have would be a lot more than 4. So this is just an artist's conception. You probably need an electron microscope or something to actually see the individual domains. But the idea is clear, is that all the material on the same grains. So I think, as an idea to explain a flat polarization spectrum, it's a pretty compelling idea because it naturally gives you one, because you just have one component, so it looks has the same SED in total and polarized intensity. But there's a lot more that we know about dust than the polarization fraction as a function of wavelength. I showed you the extinction curve from the UV to the mid-infrared and polarized extinction curve. And we also know a lot about dust emission. So you really have to say, can you take a simpler model? Can you get rid of one component completely and still explain everything we know about interstellar dust? And the short answer to that question is yes, actually you can. So showed that a single component model is perfectly capable of explaining all of the dust phenomenology that we have, from UV extinction, all the way out to long wavelength emission and polarization. that there's no need to invoke separate populations of silicon carbonaceous grains to explain anything that we know about interstellar dust. And it produces a very nice flat polarization spectrum, exactly like we see in data. I will even say that the model was fit to the blue points, but the red points were allowed to be a prediction. When you get to very short wavelengths, you start getting dominated by very small grains that have a hard time aligning with magnetic fields. So that's why it eventually falls off, because you get dominated by grains so small they can't align. Further, you'll get into the pH features. So what does this do to the AGB story I told you about oxygen-rich stars and carbon-rich stars? Well, I would argue that that story very much still holds. I mean, we even see different kinds of grains around different kinds of AGB stars. But the extra ingredient that you need is the ISM is a very dynamic place, and a lot of processing of dust grains happens in the interstellar medium, where grains are broken down, reformed, atoms are reaccreted, supernova shock comes by and vaporizes things. So very little of the dust can actually be this pure, pristine stardust that looks just like it was injected from an AGB star, but rather most of the dust in the interstellar medium looks like something that's undergone heavy processing, which includes a mixing of all of these materials. So a synthesis of all of these processes. Okay, so that's ISM implications, but I think there's also very big implications of this for the search for primordial B modes. So I mentioned that dust polarization is one of the biggest challenges for CMB. And recently, Andrew Liu, who's a PhD student at Princeton with Joe Dunkley, led a really fantastic paper as part of the SO, Simons Observatory collaboration, really digging into what is it about dust that makes it hard for CMB. And essentially what he found was that the #1 challenge about dust for CMB analysis was how much does the far infrared spectrum of dust change. So if you model the far infrared emission as a power law with some slope new to the beta, how much does this beta change from one sightline to the next? And what he found was that as this variance in beta increased, then the methods for inferring the amplitude of primordial gravitational waves on the y-axis became more and more biased. This was the critical failure mode for these CMB pipelines. And what sets this far infrared slope is nothing other than what the dust is made out of. So really, in some ways, the question of CMB foregrounds is a question of dust composition and dust life cycle and how much the dust look different in different parts of our galaxy. And if this astrodust picture is correct, that gives us some optimism that we're going to be down here on the low end of these beta variations because things reach a homogeneous end state. So I think even though these beta variations are a challenge, we have reason to be optimistic that nature will be kind here and that the actual amplitude of these beta variations will be low. And then even if they're not, Andrew has shown that we have effective ways of being able to mitigate this in our data analysis pipelines. There's also a second one, so I'll just go ahead and unite the first and second parts of the talk. This beta has also been found to have correlations with the RV parameter. And I wish I understood this theoretically. It's still a bit of a mystery how one can get this, but it seems fairly robust in data that this beta that has been fit to far infrared data seems to correlate very well with RV fit from optical extinction. And if this is true, then that means we might actually be able to leverage all of this beautiful optical data for the CMB foregrounds problem, and also learn a lot about the dust life cycle while we're at it. I'll also just plug that I've also shown that RV is connected to the magnetic field because the aspherical grain has a different cross section depending on which way you're looking at it. You can actually change the slope of the extinction curve just by these orientation effects. So there's yet another way to connect RV to dust polarization. Okay, so in the last 5 minutes, I want to be a little bit forward-looking about the future. So this astrodust picture of dust polarization has been really driven by the Planck CMB observations of polarized dust emission. And those start here at 850 microns and go longward. But all this region where all the dust is doing really interesting things, and I would like to be able to measure its polarization properties, we haven't had any platform sensitive enough to access at least the diffuse interstellar region at these wavelengths. And so I want to talk about one of the major projects, or the major project really, that I'm involved in at JPL, which is PRIMA. So PRIMA is a far infrared telescope concept. So it's currently in the proposal stage right now. So this was proposed to the NASA probe class missions. It's a new class of NASA missions that NASA's rolled out, which is $1 billion class mission. So it's intended to fill the gap between a mid-X like SphereX that I mentioned, the $400 million, and then the multi-billion JWSTs and Hubbles of the world. So $1 billion cost cap there. So PRIMA is a 1.8 meter far infrared telescope it's been cryogenically cooled and uses KITS kinetics inductance detectors technology. So the wavelength range are about 24 to 235 microns with spectroscopy imaging and imaging polarimetry running between 90 and 235. And it's just orders of magnitude improvement over the previous generation in terms of sensitivity and in terms of how long it takes to map a given region down to a certain. So where we are right now is we're actually in the final stages of competition. So we passed the first round of selection. NASA narrowed down the competition to two. So one is PRIMA, and the other was an X-ray concept called AXIS. We're writing our final reports now that are due at the end of this calendar year. And NASA is expected to make a selection in mid-2026. And the idea would be to get started on construction right away to be ready for a launch in 2031 or 2032. So with a far infrared platform like PRIMA, there's an awful lot of science that you're able to access. And I certainly won't talk about all of it or even much of it. But we have three main science teams: the origins of planetary atmospheres, where we're looking at both the water ice and the hydrogen deuteride in protoplanetary disks to be able to get a full chemical inventory of these disks and to estimate their masses. We'll be looking at the evolution of galactic ecosystems, where we're looking at the co-evolution of the cosmic star formation rate with the black hole accretion rate over cosmic time to understand how those processes are correlated and how they change either together or one lags or leads the other. And then finally, the buildup of dust and metals. So looking at these pH emission features over cosmic time, really all the way up to starting from kind of cosmic noon to redshift, 1 or so and beyond, even potentially at very high redshifts. And then using our polarimetric bands to look at the dust polarization properties in the local universe. In addition to that, we have a large range of guest observer science. So PRIMA will be an observatory with 75% of its time dedicated to guest observers, just like we all propose to use James Webb time, for instance. And so you could, we've had proposed geo ideas, everything from cosmology to objects in the solar system and everything in between. So the way I like to think about PRIMA's polarization capabilities was basically, if we were able to make a map of a galaxy with Herschel, we will be able to make a map of that galaxy in polarization with PRIMA, because we have that many orders of magnitude plural increase in sensitivity over Herschel, thanks to the cold mirror, and plus the polarization capability. So these are actual synthetic observations of the kind that we think that we will get from PRIMA for the nearby galaxy NGC 6946, where we're able to make precision polarization measurements all the way to the very edge of the galaxy, where it starts to blend in with the Milky Way foreground Sirius emission. So really, we're talking about a full census of polarization in nearby galaxies. I'll also note that each one of these polarization vectors that I've plotted on the right image of the long wavelength PRIMA band is really a 3x3 pixels. So you could imagine multiplying the number of vectors by 9 here. And this is actually a 7 by 7 polarization vector. So you can imagine multiplying the number of vectors by 49 here on the left. So it would really just be an exquisite data set. So in terms of sensitivity, we're talking about in polarization 300 to 1,000 times deeper than Sophia. We've done the calculation. If you made a polarization, full sky polarization map, essentially by mapping the full sky as fast as you could with PRIMA, that every spot on the sky would have a deeper polarization map than the deepest Sophia polarization observation. It's, again, orders of magnitude. And so one of the things that I'm very interested in doing in the case that I'm leading is to think about how we can use PRIMA to get into this question of dust homogenization in the interstellar medium, where we would in fact expect a one polarization signature if we have multiple dust components like pure stardust that exists in the ISM, where they haven't had time to homogenize, maybe immediately after a star formation event, versus something more like the Milky Way, where things have evolved to their homogenized end state, where you have a much flatter polarization spectrum. And we'll be able to make this kind of plot for each one of those pixels in those galaxies over a range of galaxies, over a range of metallicities across the local universe to really get at these questions of the dust life cycle. And so, one potential trend that we may or may not find would be to say, do we see a trend of the slope of the polarization fraction with wavelength as a function of metallicity, perhaps indicating an evolution from the more homogenized state of an older high metallicity galaxy that's had a lot of star formation to something that's more stardust dominated at low metallicities. So, I mean, this is just a very quick teaser for the PRIMA capabilities. If you're interested in any aspect of PRIMA, please have a look at our website. And of course, I'm happy to chat. So that is a whirlwind on dust and my two stories about pH growth and about homogenization of dust in the interstellar medium with some connections to cosmology of various flavors throughout. So I'll just leave out my conclusions here, and I'm happy to take any additional questions that people might have. Thank you so much. Scared silence.
Actually, several questions. So for PRIMA, how much of the sky do you think will realistically be surveyed?
So that will actually be entirely up to the general user community. So we have planned PI surveys that will not be a very impressive sky fraction in terms of that. But if you wanted to do a full sky survey with PRIMA, it is within the realm of possibility. I mean, like a few thousand hour type commitment. And so if the community says we want a full sky survey, then that is within the realm of possibility, but it's not something that we are promising with the PI science.
Another question that I had is thinking about high latitude emission. Can you do surveys that are not all sky, but you do pixel beams at cadence so that you can actually get a sense of what the degree scale variation in?
Yeah, so we will have to do a little bit of thinking about the largest angular scales that we can cover, but we scan pretty fast actually, and we're optimized for covering large areas. So PRIMA is really a mapping machine. It's not a point and stare like JWST. So I think some folks have already done some thinking about using this in a CMB context, maybe using PRIMA in a CMB deep field. I think that's completely doable. We should do that. And we have the sensitivity to do that.
I guess my last question was, you said that the dust property variations are going to depend a lot on how blended the different types are.
Yeah.
And that's actually talking about the history of parcels of gas inside the Milky Way is what you would need.
Yeah.
Like how is, it's not a very defined question, but like how would you even sort of approach modeling that if you're trying to
right. So I don't think you'll ever come up with the forward model for that. Right? So I think the point that I really wanted to make was that, if we subject ourselves to the law of averaging of very many small domains of dust grains, then there's reason to hope that the actual degree of variation of the optical properties of the composite cell is not going to be all that great. But there might be environments that have some particular chemistry or evolutionary history or whatever that might follow that assumption. And I don't know a better answer than to go measure it. It's also a lot easier to tease out those things near the peak of the spectrum than it is down. Well, I'm here all the rest of today and most of tomorrow, so find me if you want to chat about any of it. It's like running again.